So Gibbs, we've heard his name a lot so far in this class about the Gibbs energy, the Gibbs-Helmholtz equation. Gibbs came up with another rule that that's useful when thinking about phase diagrams, and that's called the Gibbs phase rule. And the formula that he came up with is a pretty simple one: F equals C plus 2 minus P. Now we need to define what all these are. F means degrees of freedom, and by this we mean how many variables can be changed. We usually are thinking about the variables of temperature and pressure, right? So number of degrees of freedom, which is variables you can change. So maybe if you can only change one variable, then you would get a line. If you can change two variables, you get a plane. If you can only change 0 variables, you get a point. Which relates to the lines and points and areas that we see on a phase diagram. C is the number of components. So this is the number of different substances you have. So we are currently, for this chapter, considering only cases where we have one component, but we'll look at 2-component systems in the next chapter. And you can even extend this to multiple, more than just 1 or 2 components, even up to 3 or 4 or whatever. And then P here is the number of phases in equilibrium. Okay, and so from this we can get, this is sort of describing what we've seen in the phase diagram that we were looking at. If we have, we're looking at only one component systems, okay, so we can say F is equal to 3 minus P. And so the number of degrees of freedom you have depends on the number of phases that are in equilibrium. So if you have only one phase in equilibrium, if you're just a solid, liquid, or gas without anything else, then F is equal to 2, which means you can change temperature and pressure. And so you get a whole area that in which that one phase is stable, and it's not in equilibrium with anything else. If you have 2 phases, then F will only equal 1, so you can change only one of temperature or pressure and have those 2 phases remain in equilibrium. And so this will give you a line. This will give you those coexistence curves that we were looking at. And if you have all 3 phases in equilibrium, F equals 0, and you get the triple point, right? So for a single substance, right, if we have just one component in the mixture that we're looking at, not a mixture because there's only one component, we see this behavior. Now this applies even to more exotic phase diagrams. So I'm going to pull up the screen and show you the phase diagram of water, but water up to very high pressures. So water under moderate pressure, normal pressures, looks similar to the phase diagram we saw for benzene. But if you get to very high pressures, the liquid and solid phases are perfectly normal, but or sorry, liquid and gas phases. But the solid phase looks pretty crazy. And so this is water, but a high pressure phase diagram. And we can see for something like water and many other substances that exhibit similar behavior, we see that in the solid phase, there's not just one phase, right? We have multiple different phases here. There's many different kinds of ice, and they're labeled by Roman numerals. So we have ice 1, that's normal ice that we're used to, but the crystal structure can change, and so you have ice 2, ice 3, ice 5, ice 6, ice 7, and so these are all different phases, but they still follow the same phase rule that we saw above, the Gibbs phase rule. So we can see any place where there's 2 phases coexisting along these lines like this, including the liquid over here, those are lines, right? So those only have 1 degree of freedom. If we have 3 phases coexisting, and we can see now there's multiple triple points here, right? Wherever 3 phases meet, there's only a single point at which they coexist. So this, we could say this is a triple point of water. When we call something the triple point, we're talking about where solid, liquid, and gas are all in equilibrium. the gas doesn't even show up on this diagram. But anyway, we can see that even these exotic phase diagrams, if there's a single component, follow the Gibbs phase rule. And so that can show you phase diagrams can be also a little bit more complicated than the ones you've seen before when you have especially when you have multiple solid phases, as we can see in water. And we can see these pressures are crazy, right? This is in kilobar. This is really high pressure. So so often you have to go to those high pressures to see these different solid phases.